Section 6.1, Part 3. Lily wants to set up an account for her new granddaughter and wants the account to grow to $40,000 over 18 years. She believes the account will earn 6% interest rate compounded semi-annually, twice a year. To the nearest dollar, how much will Lily need to invest in the account now? So to calculate how much Lily needs to invest now to grow the account to $40,000 over 18 years with a 6% interest rate compounded semi-annually, we can use the compound interest formula, which is this formula right here. So in this formula, what we're missing is the principal. That's what we're looking for, and we have the rest. What we have here, we have the future amount after 18 years. So A equals to $40,000. We have the interest rate R is 6%. We have the N, the time, is twice a year. And we have the years, which is 18 years. So that's what we have, and we're looking for the principal P. So with the interest formula, with the compound interest formula says we have 40,000 equals to P times 1 plus 0.06 divided by 2 raised to 2 times 18, which will give me 40,000 equals to P times 1.03 raised to the 36 power. If you compute that, you will get 40,000 equals to 1.03 raised to the 36th power is equal to approximately 2.89, or let's say 90. So I'm going to say P times 2.8983. Now, in order to solve, we're going to divide both sides by that number, 2.8983. Now, if we say 40,000 divided by 2.8983, we get the principal is equal to approximately $13,808. So that is to the nearest dollar. It is originally the actual amount is equal to $13,807.77. And then you're going to round it to the nearest dollar because the question is asking to round it to the nearest dollar. And that is the principal amount Lily needs to invest now in order to grow the account to $40,000 over 18 years. The next concept that we're going to cover is the number E, or the Euler number. The letter E represents the irrational number, 1 plus 1 over n, all raised to the n power, as n increases without a bound. So if you keep plugging in basic numbers 1, 2, 3, 4, 5, you will notice that you will get to a specific number very close to the number, and that number is E. The letter E is used as a base for many real-world exponential models. To work with the base E, we use the approximation E equals to 2.718282. The constant was named by the Swiss mathematician Leonhard Euler, who first investigated and discovered many of its properties. The continuous growth and decay formulas. So one of the applications for the Euler number is the continuous growth and decay formula. Continuous growth or decay is represented by the formulas A of t equals to A e to the RT, or A of t equals to the A naught, which is the initial population or initial value, e to the RT, where A or A naught is the initial value, R is the continuous growth rate per unit time or decay rate, T is the lapse time. If R is positive, then the formula represents a continuous growth. If R is negative, then the formula represents continuous decay. For business applications, the continuous growth formula is called the continuous compounding formula, and it takes the form A of t equals to the principal, P times e to the RT, where P is the principal or the initial investment, R is the growth or interest rate per unit time. T is the period or term of the investment. So if we want continuous compounding formula, this is the formula we're going to use. While the previous formula was not continuous, was done over a certain period of time, so it could be compounded annually, semi-annually, weekly, monthly, yearly, and etc. Let's look at our first example here. A person invested $1,000 in an account, earning a nominal 10% per year, compounded continuously. How much was in the account at the end of 2 years? So what do we have here? We have the principal, which is $1,000. And we have the interest rate, so 0.10. And we have, it is compounded continuously, so we're going to use the continuously compounded formula, this formula right here. And we're going to, and what else do we have here? We have the time t, which is equal to 2 years. So the time t is equal to 2 years. Now we're going to apply, so we know that the future amount is equal to the principal. We're going to use this formula again, times e to the rt, so 0.10 times 2. So if you find that expression, if you plug that expression in and find it, it is approximately $1,221.4. So it's approximately $1,221.40. That is an example for using the continuous compounding formula. Radon 222 decays at a continuous rate of 17.3% per day. So R equals negative 0.17.3, which is 0.173. How much will 100 milligrams of radon 222 decay in 3 days? So the initial amount, the principal amount is 100 milligrams, and the time is 3 days. So in this case, we're going to set it up like this. So we have the initial amount, the future amount is equal to the initial amount, e to the RT. We can use any of these. Doesn't matter the notation, so we can say A naught or we can say the principal in this case. Let me actually switch it. So I'm going to switch that to, so A naught equals 2, so A equals A naught times. So that would lead to A equals 2, A naught is 100, and then e to the negative 0.173. The reason why we put the rate negative, because it's a decay rate, so it has to be negative, less than 1, times the time, which is 3 days. And then if you compute that, I will get approximately 59.50 milligrams of radon 222 remained after 3 days based on that decay rate. Graphs of exponential functions, base 2 and base e examples. So you will see here that we have the function f of x equals to 2 to this x power, and this is the graph for it. So let me highlight it. So that is the graph of f of x equals x to the x power. And if you take the negative power, it is the same as basically 1 over 2 raised to the x power. So it's going to flip over the y-axis, and it's going to look like this. So it's going to become a decay formula. Notice how when we know that e is bigger than 2, it's 2.718282. So e, the Euler number, is 2.718282, which is bigger than 2. Notice how when the base increases, the graph becomes closer to the y-axis. So here is the graph for f of x equals to, or g of x equals x to the e to the x power, Euler number raised to the x power. So that is g of x. And notice when you take the negative, so if you say, well, g of x is basically e to the negative x. This is the same as saying 1 over e raised to the x power. So it's going to be a decay formula because 1 over e is going to be less than 1. It's positive, but it's less than 1. So this is the graph of that formula right here. And as you can see, it's still closer to the y-axis. So as the base increases from 2 to 2.718282, the graph becomes closer and closer to the y-axis. So it becomes tighter. But it has the same y-intercept as you notice here. It's 0 and 1. So that is the end of section 6.1. If you have any questions, let me know.